In this video, I am going to discuss another state space representation model example. In this example, a simple RLC circuit is given. The components are similar to the previous example, but the arrangement is different. Resistor is in here. The input voltage is Vi and the output voltage is Vout, that is the voltage across the capacitor. These are the two equations for state space representation: state equation and output equation. State equation is x dot t is equal to x plus bu, and the output equation is y is equal to cx plus du. As the first step, we have to define what are the state variable of this system. If we consider this circuit, I will consider first the current flowing through the inductor is I, and current flowing through the resistor is IR, and current flowing through the capacitor is IC. I consider first state variable as I, that is the current flowing through the inductor from the source and through the inductor. And as the second state variable, I select V out, that is the voltage across the capacitor. These are the two state variable. Now we have to derive differential equation for these two variables. If we consider di over dt, we can write it as I dot, and for the dv out over dt, we can write v out. As the step 2, we have derived differential equation using derivation of these two selected state variable. First, I consider this loop. I consider it as A and this loop B. Consider loop A, and I will apply KVL for that loop. Vi is the voltage source, Vi, and this inductor is a load, minus voltage across the inductor is L times di over dt, rate of change of current, and voltage across A and B, I write it as VAB is equal to 0. If we consider the voltage between A and B, it is equal to voltage across the resistor or voltage across the capacitor, and it will be equal to V out. Then for the VAB, it is equal to V out. That is a selected state variable. Then we can write VI minus L times di over dt minus P out is equal to 0. And this is the derivation of one state variable di over dt. Then we can rearrange L times di over dt is equal to Vi minus V out. For this part, I can write I dot is equal to 1 over L Vi minus 1 over L V out. From this equation, we can derive first differential equation I dot minus 1 over L V out plus 1 over L Vi. This is the input for the system, and this is the state variable. This is the derivation of one state variable. Now the first differential equation is complete. Now we have to find the second differential equation. For that one, I consider this node A, and I will apply KCL to that node. For this node, incoming currents are I, and the outgoing currents are IR and IC. I is equal to IR plus IC. I will write for the IR, we can rewrite it from known terms. IR is current flowing through the resistor, and it can be write as voltage over impedance. Voltage is V out, V out, and the impedance is R. Same as this one, for the IC, we can write from known terms. IC is the current flowing through the capacitor. We can write C times dV out over dt. If we consider this equation, we can see a derivation of V out. Then we can write C times dV out over dt is equal to I minus V out over R. dV naught over T is equal to V naught dot. Then V out dot T is equal to 1 over C times I minus 1 over RC V out. This is the second equation, second differential equation. These two are the state variables. We derived two differential equation. Now we have to represent these two differential equation according to this format. According to this, x dot t is equal to ax plus bu. Now we can write it x dot t is equal to ax plus bu. For the x dot vector, we can write I dot and v naught dot is equal to, we have to define matrix of A, and state vector is I and V out, plus we have defined what is the value of B matrix, and input is Vi. The first equation is I dot t is equal to minus 1 over L V out plus 1 over L V in. There are no any items. 0 minus 1 over L, 0 into I minus 1 over L into V naught, and 1 over L into Vi. Now first equation is complete. Now we have to consider second equation. V out dot is equal to 1 over Ci, 1 over C here into I, and 1 minus 1 over RC into V out. There are no any input voltage terms, then it will be 0. And if we consider output, I consider V out is the output variable of this system. Y is equal to Cx. Then we can write C vector 0, 1 into I and V out, that state vector. This is the output equation of that electrical system, and this is the state space representation. This is the matrix A, this is matrix B, state vector and input vector, and this is the output equation representation.